All right, guys, welcome to Quarantine Math Analysis for March 30th. Last week we talked a lot about derivatives. We went through pretty much the whole gamut of them, right? We talked about the idea behind them. We talked about the kind of crazy complex way of solving for them. We talked about how to graph kind of the end result of the derivatives, taking that derivative, finding the slope of a point, and how it makes a tangent line. We talked about all these different things. Now, while it's important to get practice with and important to, have a little bit of mathematical understanding about how we come to getting the derivatives by hand, kind of the long way, quote unquote, what we end up finding out is there are actually some rules about derivatives that we can follow to kind of skip through the difficult hard part and be able to find out the derivative a lot easier. Going from that really complex work last week to just some nice shortcuts through derivative rules. Now, what I've got before us here is four functions. On the left are four original functions, and on the right are the derivatives of those functions. What I want you to do is take a look at this and, pause the video here in a second if you want, but I want you to see if you notice a pattern between these four functions and their derivatives. Do you see any way that, if you look at how these numbers transitioned, that if I wrote a different one on here, if I wrote like 4x to the 7th plus 3x to the 6th, and I wanted to find its derivative, see if you would be able to figure that out. See if you'd be able to take what we have there and then kind of see what it would be, guess what it would be. Pause the video if you want, take a minute to think about that. We're going to go over what it is here in a few seconds, but if you'd like to try it out yourself, go ahead and pause, think about it, and then you can check your work. All right, well, hopefully you have an answer. Hopefully you tried that out. Maybe you just kept watching the video. Who knows? But here's the trick. Let's start by looking at the first derivative. Sorry, my camera keeps sliding down a bit here, so apologize if it's wobbly. I'm trying to hold it up. We have 7x squared plus 9x. Well, we have 7 turning into 14 and 9 staying as 9. So that seems a little weird, but okay, maybe that's something that's kind of the same happening in our next one. This number doubled and the second number stayed the same. Maybe that's a pattern. Well, in our next one we have 9 and it turns into 45, so yeah, that's a little bit more than doubling. And 5 turned into 15, and that definitely didn't stay the same. So in this one, if we look, how'd that number change? Well, 45 is 5 times bigger than 9, right? 15 is 3 times bigger than 5. Are you noticing anything amongst those that might be looking at what a pattern actually could be? You might have saw it. That pattern has to do with the variables and their exponents. Take a look here. This exponent is going to tell us how many times we need to multiply this number for the derivative. See there, 7 times 2 is 14. What's the exponent just on an x? Well, that's a 1. That's x to the first, right? 9 times 1, 9. We have the same thing happening here. 9 times 5 is 45. 5 times 3, 15. Let's see this. 6 times 3, 18. Well, did I just forget to write the second part? I don't know. Does this have a variable and an exponent? It doesn't, right? So technically, that has a variable with an exponent of 0, because it doesn't exist. 13 times 0 is nothing. That's 0. We don't write it. 3 times 8 is 24. 5 times 5, or actually negative 5 times 5, is negative 25. So we can probably presume with this new function what the coefficients at least are going to be. And then we'll talk about the variables next. 4 times 7, well, that's going to be 28. 3 times 6, that's a positive 18. So we know the coefficients, but what are the variables going to be? So that's what we're going to look at next. Let's see how our variables changed. Right here we have x squared, and here we have an x to the first. Well, that turned into an x and nothing. Okay, maybe we can see a pattern there. Maybe we just lose the variable in the second one. I don't know. If we look at this next one, we have x to the fifth. It turns into x to the fourth. And then we have x to the third. That should have turned into x squared. But that's my bad for writing that incorrectly. Here we have x to the third that turned into x squared. And then we explained why that doesn't have anything happening to it. And then we get an x to the eighth that goes to the seventh, and an x to the fifth that goes to x to the fourth. So what pattern are we noticing throughout all of these with their variables? Every single time this variable has an exponent that is going down by 1, right? Like 2 turned into 1, the 1 variable it had went down and turned into 0. So we're taking away 1x each time. 5 went down 1 to 4, 3 went down 1 to 2. 3 went down to 2 again. 8 went down to 7, 5 went down to 4. So what are we going to be looking at here? 7 is going to go down to x to the sixth. And 6 is going to go down to x to the fifth. So for all of you guys who over the past week have been thinking, my goodness, this derivative stuff is insane. How long is it going to take to do these problems? How complicated are these problems going to be with all of these functions and squaring it or putting it to the third and x and delta x's? Well, guess what? We can kind of forego all of those formalities in finding the derivatives because we know these derivative rules and these derivative shortcuts, if you will. Rules is the proper term for them, but it's good to think of it as a shortcut. This is a quick, simple, and easy way to find a derivative of any given number. So what I'm going to do is I'm going to get our packet, and I'm going to take a look at the first page of the packet, and we are going to do a couple of these, and then I'm going to ask you guys to try out finding the derivative of a few of them too, using this shortcut method. So this is question 1 and question 4 on your packet on the very first page. We're going to go ahead and find the derivative using the rules that we had from before. So we're going to take each number and we're going to multiply it by the exponent of the variable it is with. So we're going to start with probably the trickiest one whenever we don't have a variable. So here's what I want you to think. We have 8 times, well, what's our variable there? We don't have an exponent, so we don't have a variable, so its exponent must be 0. 8 times 0, 0. Nothing. We don't actually have to include that in our final answer, right? Now let's take a look at this. -4 times 3, well, that's going to be -12. And then what happens to the variable? It goes down by 1, so x squared. Then here, 2 times 8, well, that's going to be 16. And then 1 less than 8 for our variable is going to be x to the 7th. So this is our derivative, -12x squared plus 16x to the 7th. If we take a look at the next one, we notice a slight difference here. That slight difference being we have a negative exponent. But the great thing is these still function in the exact same way. We can do this. 3 times -4. Well, that's -12. And then whenever we talk about what is 1 less, well, what's 1 less than -4? We have to think about this like a number line. We're going down one more. We're subtracting 1. So that's going to be negative 5. And then next up, the coefficient. Well, what's the coefficient here? It's a 1, right? Even though we don't see it, it's a 1. 1 times 4. So 4. X to the 1 less exponent to the third. And then here, negative 3 times, what's the exponent there? It's 1. So negative 3 times 1 stays negative 3. And then if we have 1 less exponent than x to the first, is x to the 0. So it just goes away. It's not written. So the derivative to number 4 is this right here. Didn't mean to draw through that 16. Meant to just kind of, box it. But here we are. So these are our two derivatives on 1 and 4. What I want you guys to try out is numbers 2, 3, 5, and 6. Try to apply this same thought, this shortcut, what's called the derivative power rule, to the 4 problems that I had listed there. If you have any questions, feel free to email me. We will talk about any of those problems you have difficulty with in tomorrow's video. But otherwise, I'll see you guys then.